This is the second Lewis structures video and the first video dealing with some exceptions. There's two different exceptions we want to come to terms with in terms of Lewis structures. And so the first one, electron deficient exception. So this is where the central atom has fewer than 8 electrons in its valence shell. And so this occurs with a few different compounds. A few different atoms typically give rise to this sort of thing. And the first one here is a molecule known as boron with the formula of BH3. So iupacine would be boron trihydride. And so here's boron in the middle, and it's bonded to 3 hydrogens. And each of those bonds is actually a single covalent bond. So there's no double bonding there. And so if you count the electrons around the boron atom, there will only be 6 electrons associated with boron. And so that is an example of electron deficient. Boron, by the way, is a common precursor for a lot of organic synthesis reactions. Part of the reason for that is it's quite reactive, and it's quite reactive because it has that valence shell that is not filled. So let's look at how these examples work. So the exceptions in this case are the electron deficient valence shell, and you should be familiar with the two exceptions I'm going to mention right now. So we've kind of already looked at one. Well, we'll look at it again. But we've learned some guidelines on determining a number of bonds, number of lone pairs, that sort of thing, and allow us to draw Lewis structures. So do that now for these two structures, beryllium chloride and boron trifluoride. So maybe pause the video and calculate the bonding pattern and see if you can draw the Lewis structures. So for beryllium chloride, BeCl2, when we do our calculations, we come up with 16 valence electrons, 24 electrons needed, assuming that boron requires 8, and that gives us 4 bonds. So when we draw beryllium chloride, it was going to look something like this. So we're going to attach the 2 chlorines. We calculated 4 bonds, so there's the 4 bonds, and there's the 4 lone pairs around the chlorine. So we've satisfied the octet for beryllium with the 2 double bonds, and we satisfied the octet with chlorine with a double bond to each chlorine and 2 lone pairs. If we do it for boron trifluoride, it was going to look like this. BF3, 24 valence electrons, 32 electrons needed. Again, calculating as 4 bonds, assuming, once again, that the boron requires 8 electrons in its valence shell. So now we can go ahead and draw this. And so there's our boron. It's going to have 3 fluorines bonded to it. And because it's 4 bonds, one of those bonds must be a double bond. And so then we put out our 8 lone pairs. And so there they are. And so we've satisfied the octets or everything. 1 double bond, that actually means there's resonance. So we would in fact have to draw 3 different structures for boron trifluoride if this was in fact the structure. However, this is an exception. That's the topic of the video. So experimental evidence suggests that neither of these 2 molecules contain any double bonds. So these 2 atoms do not follow the stable octet rule. Again, bond energy studies quite easily tell you the nature of the bonding, and those studies indicate there can't be any double bonds in these 2 molecules. So the actual Lewis structures are a little simpler. So with beryllium chloride, it's BeCl, Cl. It's just single bonds, and we just satisfy the octets with lone pairs to the chlorine. And again, so our calculation for valence electrons is 2 plus 14 or 16, and if we count our electrons, 2, 4, 6, 8 around this chlorine, 2, 4, 6, 8 around this chlorine, that's 16 electrons, and beryllium only has 4 electrons. So that's a stable configuration for beryllium chloride. And boron trifluoride is much the same. No double bonds, so they must all be single bonds. And we satisfy the octets of fluorine, and we're finished with it. And so again, we predict a double bond, but the data does not support the presence of a double bond. So that's something you do need to try to remember. You are expected to know that both beryllium and boron form stable molecules where the central atom is electron deficient. That is just kind of interesting, again, based on reactivity. So the borane BH3 with its 6 electrons around the valence shell can still actually form a bond, and it does this with things like ammonia, NH3. Now NH3 is interesting because it has 3 hydrogens on it, and it has this lone pair. And so the lone pair of NH3 actually is what allows the borane to attach to the ammonia. And so when that happens, we get this bond forming from the electron pair of the ammonia, and that's actually known as a coordinate covalent bond. Another name for it is a coordinate dative bond. And that gives rise to this borane ammonia adduct. And these particular molecules, these adducts, especially ones containing boron, are becoming quite important because they are potentially going to be a really good source of fuel for hydrogen fuel cells because they're so hydrogen rich. So you can drive a reaction with this adduct, get a disposable product, and then the process generate hydrogen, which will drive the fuel cell. Main thing here though is, so we've seen borane as electron deficient, but it doesn't mean boron can't form another covalent bond. Boron is still capable of accepting or holding any electrons and forming a stable octet. So it can still happen. So another atom that behaves like boron is, unsurprisingly, aluminum. So directly below boron on a periodic table. And so if we were to go through the process and generate a Lewis structure for aluminum, we're going to, first of all, realize it's polar covalent, not ionic, even though people might think it's ionic, metal with a nonmetal. It's actually polar covalent because of the delta En. And we would then determine the bonding pattern using our guidelines, and we'd come up with this as the bonding pattern. And so we'd seed 4 bonds, but then we remember that aluminum is electron deficient, or can be electron deficient. So aluminum chloride is going to be much like boron hydride, trihydride, or boron trifluoride, in that 3 bonds from the aluminum only, and aluminum ends up being electron deficient. And so boron trichloride, or aluminum chloride, sorry, is a stable compound. And the aluminum hydride ion then is going to be much like boron behaving as in that adduct, in that the calculations we would do to determine things indicate 4 bonds. And this, in fact, is what happens. And so we would go draw our Lewis structure now. So aluminum out there, and it's bonded to 4 hydrogens, so we just bond them. And remember, it's an ion, so we put the square brackets. And so this aluminum hydride ion is a stable configuration. So once again, just pointing out that the octet rule is very useful in coming to some form of understanding of how things bond. But it's a fairly simple rule. There's always bound to be exceptions, and so boron and aluminum are less predictable and end up being exceptions, but at the same time can satisfy the octet rule in terms of Lewis structures. So as I said, you just need to make sure you remember beryllium, boron, aluminum. Exceptions to the octet rule in some instances, and then boron, aluminum, not always. The last one I want to talk about then is another quite common molecule, and this is nitrogen monoxide, NO. So once you just pause the video and quickly determine the bonding and lone pairs and etc. for nitrogen monoxide and see what you come up with. So if you've gone ahead and done that, you would have determined this. And so the question marks are there because this is definitely an exception. 11 valence electrons should be the first one. So an uneven number of valence electrons. We've never seen that before. So what we have here is a free electron. If you do the bond calculation, it comes out as 2.5. Well, again, that's clearly indicative of an exception. So let's go ahead and draw this now and see what we come up with. So N is definitely bonded to oxygen. Now, if we want to put out our valence electrons, we already have 2 here. So let's satisfy the octet for oxygen. So now that's 8 for oxygen, and that's 8 in total. We only have 3 more to go. 1, 2, 3. And notice nitrogen only has 5 electrons. So that's not a stable configuration. So what else can we do? Well, let's give it a double bond to see what happens. So double bond, now we have 8 around the oxygen and 3 around the nitrogen again. And so that would not be as stable. And how about a triple bond? Well, now we've satisfied the octet for oxygen. And now we can't do that because we now have 9 electrons around nitrogen. So that's not going to be the case. So we're back to this one. And so this one is the closest, and this one is actually going to be the plausible structure, but we have to make one change. And that change is that electrons pair up. And so we have a single electron pair, and then we have this lone electron. And so that is what makes this a radical. It's known as a radical, or it has a free electron, and radicals are very reactive. And so if you want, you can look up nitrogen monoxide and see it's a very common, actually very common molecule. It's also very reactive, so it's used in a lot of different ways due to its reactivity. But it is just another example of an electron-deficient atom, and that's the nitrogen as a part of nitrogen monoxide. And that concludes this video.